To verify if this would be even remotely possible, we first calculated the escape velocity of a person, using the escape velocity formula, which is the square root of 2gm over r, g standing for universal gravitation, m standing for the mass of the planet, and r standing for the radius of the planet. Assuming that we are on planet Earth, the universal gravitation would be 6.67 times 10 to the negative 11. The mass of Earth would be 5.97 times 10 to the 24, and the radius of Earth would be 6.38 times 10 to the 6. When calculating this, we found that the escape velocity of Earth would be 1.12 times 10 to the 4 meters per second. Using the escape velocity, we calculated the energy needed to leave Earth using the kinetic energy formula, which is 1/2 mv squared. Plugging in all the information we know, including that mass is around 80.7 kilograms for an average weight of an Indian male, we found that the energy needed to punch someone into space is 5.04 times 10 to the 9 joules. Next, taking the average height of an Indian male, which is around 1.69 meters, we found that the wingspan of an Indian male would be approximately their height plus 0.05 meters, which gave us 1.74 meters. To find the length of one arm, we divided 1.74 in 2, which gave us 0.87 meters. Using this, we found the dimensions for the forearm and the hand of a person with height of 1.69 meters to be around 0.436 meters. From this, we calculated that since the length is 0.436 plus 0.434 meters, we found that the distance between the arm and the person is 0.615 meters to calculate the distance that goes into force. Using this distance, we found that work equals energy, which also equals force times distance. So, using the previous energy that we found, we plugged in and calculated the force as 8,189,869,343 newtons. This would be unrealistic because in real life, the amount of force would just end up ripping a hole into a person's body instead of actually sending him into space. However, we decided to go the extra step and find out how much force could one arm actually deliver. And so we went on to find the acceleration of one arm. To do this, we calculated 5 measurements of time that it took for the arm to connect with the person, and we found the average of time was 0.3 seconds. From this, we calculated the acceleration given the distance and the previous time that we just calculated, and got the acceleration to be 13.67 meters per second squared. From this, we could find the force of one arm, which is force equals mass times acceleration. The mass of one arm is approximately 5.7% of the total mass of the body. So we found taking 80.7 kilograms as the average weight of an Indian male, we found the mass of one arm to be 4.6 kilograms. From this, we calculated the force, which is 4.6 kilograms times 13.67 meters per second squared, and we got the total force delivered by one arm to be 62.87 newtons, which is the equivalent of getting hit in the stomach with an overweight cat, which would not nearly be enough to send someone into outer space.
Using the maximum speed that an arrow can reach using a recurve bow, which is the same bow that the man uses in the scene, and the mass of one recurve arrow, we calculated that the momentum of the arrow is 89.11 kilograms per meters per second. Now, to find the momentum of the men who were approaching the arrow, we found the mass of an average Asian man and his armor to be 77.7 kilograms and the maximum speed of a jogging man to be 2.68 meters per second. Now, using these values, we found the momentum of the man to be 208.23 kilograms per meters per second. Using these values, we were able to prove that the momentum of the arrow is less than the momentum of the man. This proves that if the man were to be impelled with the arrow, the man would still have enough momentum to continue jogging forward, since the arrow does not have enough momentum to even stop the man. In order to find the total force that the spider web could withstand, we first found the tensile strength, which was 120 pounds per square millimeter. Then we multiplied it by the area of the spider web to find the total tensile strength of the spider web that Spider-Man was hanging from. Then we found the gravitational mass of Spider-Man and compared it to the value of the tensile strength. The tensile strength of the spider web was significantly higher than the gravitational mass, meaning that this situation would be impossible.
To calculate the momentum of how much a rhino would apply to a human, we first took the average weight of an African rhino, and they weigh about 1,800 kilograms. We also took the maximum speed of a black rhino, and they can run up to 34 miles per hour, and we converted this to meters per second, which turned out to be 15.278 meters per second. And we figured that the momentum would equal 27,500 newtons per second. We next calculated the momentum that Black Panther received in this movie when he was hit by the rhino. And to calculate this, we set up an equation, which was the force applied times 0.01 seconds. And the force applied was 27,500 newtons per second. And this came out to be 2,500 newtons, or 59.25 G. And a typical person can handle 5 G, or 47 meters per second squared. So the end question is, can a human withstand the momentum applied by a rhino? The answer is no. They would die as soon as the rhino hit them because there's so much force being transferred through their body. In this movie, it was shown that the force was transferred through the body of Black Panther, and he was perfectly fine. He got back up. However, an average person can only handle 5 G, but in the movie, Black Panther handled 59.52 G, which is almost 10 times more. So in the end, the human would die.
Alright, so Kalakalapu 2. We are going to try to disprove the possibility of one of the characters, Anjali, being able to break glass with her voice. So first we need to find out the average frequency of a typical adult female's voice. The voice speech of a typical adult female will have a fundamental frequency from 165 to 255 Hz. Then we had to find out the frequency required to shatter the glass shown in the movie, which is approximately 550 Hz. Through extensive research, it was concluded that while breaking glass with your voice does take extensive training and practice, it is not exactly impossible, and therefore we cannot assume that Anjali was unable to break the glass just yet. So assuming Anjali had trained her voice to have a frequency of around 550 Hz, we will be using the formula wavelength equals velocity divided by frequency to estimate the velocity needed to achieve glass breakability. A frequency of approximately 556 Hz is needed, with an intensity of 105 decibels to break the Indian framing glass featured in the movie. First, we need to identify our known variables. Wavelength is equal to 0.017 meters. The frequency, as mentioned previously, is 556. If we plug in 0.017 equals velocity divided by 556, we get 0.017 times 556 equals 9.452, therefore making velocity equals 9.452 meters per second. Here is an image from the movie clip of Anjali screaming. Surrounding her are sound waves shown in a sort of Doppler effect. This screenshot was taken exactly 1 second after she started screaming, and the sound wave was released. Now we want to be able to scale the image so we can measure the distance traveled by the sound wave in 1 second. If Anjali's height is approximately 1.65 meters, this length right here is also 1.65 meters, which means the entire length of the sound wave has traveled under 1 second is around 2 to 2.3 meters. If we can identify the height of Anjali, we can approximately scale the image, thus saying 2.3 meters would be the velocity needed. 2.3 meters per second. Knowing this, we can plug it back into the formula of wavelength equals velocity divided by frequency. The frequency would have to be 135.29 meters per second, which is too low a frequency to break glass. Therefore, the physics in the scene is incorrect.